Alright, we've proven that closed and bounded implies compact, but does compact imply closed and bounded? The answer is yes, and we're going to prove that. So let C be compact. Let UI, cover Rn, all of Rn, with UI is going to be no. Yes, no. J. Uj is going to be product from I equals 1 to n of Aij Bij. And this is true in Rn. For example, you could do, let's just take all possible open boxes. Then that's going to be cover of Rn because every point is in some open box. This isn't true in every single space, but if you study topology, you'll come across that. Then U has a finite subcover of C, and this will be, we'll call it Uj, j equals 1 to m, so of C. So for each one of these j's, let mj be the minimum for all I between 1 and m. No. I'm going to switch this around. Let mi be the minimum of Aij. So we're taking, we're looking at the ith index of each of these UJs and taking the smallest leftmost index. And let Wj be the max of Bij. And of course we're using M for mini and W for wumbo. So then C is contained in the union from j equals 1 to m of Uj. But this is going to be contained in the product from I equals 1 to n of miwi. And that's because if you look at the union of the UJs and you look at what this set looks like in the ith coordinate, it's going to be the union of all the intervals Aij, Bij, where j ranges from 1 to m. And so what's going to happen, wait, hold on. Did I mess product ij? So the first index, yes. Okay, this is good. Okay, so you're looking at all of these, you're looking at these intervals Aij to Bij, where j ranges over 1 to m. And so if you take the union, you're taking the union of all these intervals, and the left end of that union is going to be the minimum one, and the right end is going to be the maximum one. So the leftmost boundary will be mi, and the rightmost will be wi. So we're going to have containment. And this will hold for every single index. And so the union of the UJs is indeed contained in this product. So we found an open rectangle containing C, and that's what it means to be bounded. Thus, C is bounded. So that wasn't too bad. Hopefully, compactness or closeness won't be too bad. It's a little worse. Let's see here. So, to prove closedness, let X be in C complement. So, instead of proving that C is closed, we're going to prove that C complement is open. So we need to find an open neighborhood around X which does not intersect C. And we're going to have to use compactness. Alright, so for any Y in C, let UY be an open rectangle around Y of this form. You take each yi and you subtract and add delta y, where delta y obviously needs to be greater than 0, but it's going to be less than, and then the obvious choice, norm of x minus y over 4 square root of n. Now where does this come from? Basically, this comes from you sort of work backwards to find this. Or at least what I did is, I'm like, okay, so I want to get a particular result. In order to get this result, I need delta to be less than something. What do I need it to be less than in order for this to work out? And you do the algebra, and you find out that this is what you need. And note that, so why do we choose this? Just as a hint, the square root of n times delta y is going to be less than norm of x minus y over 4. And we've seen before that we use these sorts of, this thing square root of n times delta y, things looking like this come up when we end up doing estimates of things in open rectangles. Okay, but anyways, if we look at this uy, or y is in C, is an open cover of C because each element of C is contained in one of these intervals. So there is a finite subcover uy1 through uym. This m does not need to be the same m as before. Alright. Anyways. So, let u... So, what we're going to do is, instead of proving that x contains a neighborhood not intersecting C, we're going to prove that x contains a neighborhood not intersecting any of these uyj's. So what we want to do is we want to choose our neighborhood. So this is going to be, again, the product from I equals 1 to n. We're going to do xi minus delta, xi plus delta, and how do we choose delta? Where delta is going to be positive, it's going to be less than 1 over 4 times the square root of n, similar to what we had before. We're going to multiply this times the minimum over all j between 1 and m of the distance between x and yj. And then what this is useful for is that, so for all j, square root of n times delta is going to be less than norm of x minus yj over 4. That's why we chose the minimum, so that this inequality would hold for every single j. So, let's see here. I claim that the intersection of u with uyj is empty for every single j. So given any particular j between 1 and m, let y be any element of uyj. We want to prove that y is not in u. So to prove that, we're going to prove that y is not equal to any particular element of u. So let z be any particular element of u. Then we have a calculation. This one's going to be a little messy. We take the distance between z and y. So this is going to be greater than or equal to, we're going to use the reverse triangle inequality. You add z and you add x and subtract x and then apply the reverse triangle inequality. And now, because of how the reverse triangle inequality works, you can remove the absolute value signs on the very outside and keep what you have on the inside and use any order you want. This is not right. This should be x minus y. Okay, so x minus y minus x minus z. So then this is greater than or equal to, we do the same thing for x minus y. But instead we do x minus yj, yj minus y, minus x minus z. So then this is greater than or equal to, so we've got x minus yj minus y minus yj minus x minus z. Alright, so then this is going to be greater, wow, my laptop screen keeps moving around. It's going to be greater than or equal to, we can keep the x minus yj for now, minus, now, let's see here, this I believe is strictly greater than, I hate this, why does it keep moving? This is going to be strictly greater than. Actually, you know what? I'm going to move this up a little bit, just in case that helps. It's going to be y minus yj. Y is in uyj. And so, in each index, remember the uyj goes from yj minus delta y to yj plus delta y. So the distance between yi, the difference between the ith index of y and the ith index of yj must be less than delta y. So this is sum from I equals 1 to n, and now we have delta yj squared. I think I misspoke there, but this is what it should be. This is true because the radius of uyj is determined by delta yj. So we have this, then we subtract the sum from I equals 1 to n. Now x minus z, z is in u, and u, each coordinate has radius delta, so we can replace this with delta squared, 1/2. Alright, so now what we have is we keep the x minus yj, and then we're going to get minus square root of n times delta yj minus square root of n times delta. This is going to be greater than or equal to, again, we still have this. Now we chose delta yj such that square root of n times delta yj is less than norm of x minus yj over 4. So if we have a minus, then this is going to be greater than minus norm of x minus yj over 4 minus, and then again we chose delta so that square root of n times delta is less than norm of x minus yj over 4 for every single particular j. And so this is minus x minus yj over 4 again. So we have 1 times x, so x minus yj, if we take the norm of that and factor that out, we get 1 minus a fourth minus 1/4. So this is just 1/2 norm of x minus yj. But the norm of x minus yj is going to be strictly positive because why is that? That should be pretty big, actually. Yeah, the norm of x minus yj right, because x is not in A and yj is in A. So it has to be greater than 0. Alright, so this is strictly greater than 0. And now looking back on this, all we needed is that z is not equal to y. So all we need is that this is strictly greater than 0. And the first time I was doing this, I tried, instead of having the 4s here, I tried doing 2. And then I ended up with norm of x minus yj minus a half norm of x minus yj minus a half norm of x minus yj. And so I got that that's equal to 0. And I was like, well, wait, if I have greater than or equal to throughout this entire argument, then that only proves that the norm of z minus y is greater than or equal to 0. And that's not enough. We need strictly greater than 0. However, looking back on this, the way that we chose these neighborhoods, all of these deltas are strictly, because of how these radii are chosen, we get strict inequalities along the way, so we could have gone with that. We still would have had strictly greater than 0. So it's not necessary to use the 4s, we could have used the 2s, but this works as well. In fact, you can choose any number larger than 4 if you want to make this distance between z and y as large as you want, or as close to norm of x minus yj as you want. But anyways, I'm getting sidetracked. What's important is that z is not equal to y. This holds. Okay, so now we have to sort of work backwards and figure out what this tells us. So this holds for all z in U, and so that tells us that y is not in U. And this holds for all y in UYJ. So the intersection of U and U, whoa, that was weird. I think I'm going to have to scroll up, or let my, here. UYJ, this intersection is empty. So the intersection of U with the union from j equals 1 to m of UYJ must also be empty, because this intersection is empty for every particular UYJ. And so the intersection of U with C is empty. because C is a subset of the union of the UYJs. Alright, so given X not in A, we have found a neighborhood U containing X which does not intersect with C. Such a U exists for all X not in, or for all X in C complement, so C complement is open. Thus C is closed. Hence, the fact that C was compact implied that C is closed and bounded. So that was kind of a tricky argument that we had to use for the closedness argument. Let's see here, I ended up looking up online for a few hints on that, on just how to make everything work out. You can do it visually and it looks nice because, here, let's just draw a few pictures. We're done with the exercise, but I'm just drawing a few pictures. So basically you take X over here, and then you take C, and then for each Y you get a UYJ, and then you get a finite subcover after you take your cover, and then you find U, and then given any, so this is sort of what it looks like. The distance between Z and Y and YJ. So you want to prove that the distance between Z and Y is greater than 0 for every single let's see here. So let's see here, this thing right here is C and this is U. Okay, so what we're doing is we want to prove that the distance between Z and Y is greater than 0. We know things about the distance between X and YJ because they both lie in different sets. I might have called CA back in the proof at some point. So we know something about the distance between X and YJ. We know something about the distance between X and Z because of the radius. We know something about the distance between Y and YJ because of the radius of YJ. And so, we've proven, and so you can use those what you know about those distances to prove something about the distance between Z and Y. And that's why the triangle inequality is useful. Because if you don't know the distance between two things, you can find other points involved about which you know the distance between those things, and you can sort of connect the dots. And I sort of like these sorts of arguments for that reason, because you can think about it visually. But anyways, we've done the exercise, and yeah, that's it.